the timestamp on all the files. So as long as you stop editing any files after the deadline, the TA should be able to do, when they are doing their reading, they will be able to go inside your home directory and look at the timestamp and figure out whether you've complete editing before that due date or not. Right? So to simply stop editing or uploading any files to the server, then by the time it's due. Right? That's essentially how you submit your fixed rate. You don't have to, other than putting all the files on the Georgia server, you don't have to physically submit anything. Okay? Now let's continue with our discussion on okay, so this is what we talked about last time. We talked about the storage hierarchy, then we talked about the RAD model, the hierarchical storage structure in a computer. What we're going to talk about today is the non-volatile storage media, which is the disk. So here is what a magnetic field disk looks like, hard drive, or typically known as. So essentially you have this what we call magnetic surface. So different from your main memory and your cache, which represent 0 or 1 bits using positively charged electrons. Disk use a totally different physical property to represent your data, right? So at the end of the day, you basically need to represent 0 or 1 bits, essentially. So the way that this has done it is to do it using this magnetic surface. Magnetic surface can be quote-unquote charged to represent north or south, right? So that's what we know, right? So any magnetic field has those two directions, and basically hard drive utilize that fact to store 0 or 1 bit. And the benefit of doing this is that the magnetic field is quote-unquote persistent, meaning even if you lose power to your system, these information are kept still there forever, right? So that's why hard drive is non-volatile. Hard drive is non-volatile for that reason. That being said, we still need to figure out how this data, right, 0 or 1 bits, sequence of 0 or 1 bits are organized on a hard drive surface, So it's a cylinder shape, like that. And each surface is organized into multiple tracks. A track essentially is all the areas, surface areas, that have same radius to the center of this cylinder. So this is the center of the cylinder. A track is basically defined as all the surface areas that have the same radius to this center. So it's a circle, right? It's a circle. And then you have this arm represented by that red beam. This is what we call the arm of the disk. The arm is able to translate a magnetic field surface, meaning north, translate to electro signal, meaning a 1 bit in your memory, in main memory. So ARM is able to do that translation. Okay? So that means that the way you read data or write data back to this is to move the arms around this surface. So you align the head of the arm to the surface area that holds the data you would like to read. Then you let the ARM do the conversion, and then you have data transferred from transferred from disk to your memory. So that's a high-level idea. Okay. So this basically represent a particular, different set of values. These are in numeric values, but imagine they are represented as binary 0 or 1 bits on this hard drive surface, right? That's kind of the idea. And the way you're gonna read it is, suppose that's where your data is. The way you're gonna read it is you're gonna move the ARM to align to that track, and then you also need to rotate the track such that the area holding your data that you want to read is right below the head of the ARM. Does that make sense? So there are two movements. One is to move the ARM in and out so that the head of the ARM is aligned with the track that has your data. But that's not enough, because track is a circular shape, right? Once you align the ARM to that particular track, you also need to wait for the track to rotate such that the area that has the data that you are trying to read from is rotated right below the head of the ARM. Then the head of the ARM is able to do the conversion, meaning it's able to detect what's the magnetic field on that particular area. North translate to 1, the other direction translate to 0, meaning translate to positively charged electron or negatively charged electron, or simply not charged. Does that make sense? That's how this. It's an oversimplified process, but that's essentially what's going on whenever you are reading data from your laptop disk. So far so good? Okay? So, another point is that data on a hard drive surface is organized in this logical unit called block. A single block typically is either 4 kilobytes or 8 kilobytes or 16 kilobytes for modern hard drive disks. So a block is nothing else but a consecutive area, surface area from the same track. So for example, you can imagine each of these small segment line here represent a single block that's either 4 kilobytes or 8 kilobytes or 16 kilobytes. And the way you read data or write data to the disk, read data from or write data to, is always in the unit of block. Meaning, even if you try to read just 1 byte of data from hard drive, you have to read 1 block of data containing that byte. So you always operate on this unit of blocks rather than on single byte. So that's another thing that you need to pay attention to. Okay? So this introduces this problem of data transfer between memory and hard drive, right? So the abstraction of the model we're dealing with is you have this processor, and this processor has cache, which we ignore for this discussion. Then you have your random access memory right here, that's your memory, 8 gigabytes, 16 gigabytes, depending on how big your memory is. And then you have this non-volatile disk storage. The observation is oftentimes you have data that's much larger than the memory you have, right? Like Google obviously has tons of data that's way larger than the memory a single machine can hold. So they have to store this data somewhere on disk, on some permanent storage media like disk, and only fetch the data that's needed from disk to memory when you need to operate over that data. And this introduces the problem of data transfer. This introduces the problem of data transfer between disk and memory. If you look at the running time and the size of data you need to fetch to memory, you will observe something like this, a curve like this. What it means is the runtime is roughly linear to the scale of your data size until you reach the boundary of your memory size. So before this, we are assuming all the data are pre-fetched into the memory, and they are loaded into your memory space in your RAM. After that point, this is when your memory is not big enough to hold all the data you want. At this point, but your program or whatever you're doing, your operating system, needs to fetch more data to memory, but you run out of space. At this point, what happens? Well, at this point, you need to kick some data out and bring some data from disk back in memory, and you keep doing this. This is when you notice a sudden jump in cost in terms of running time because of this data transfer cost. Okay? So I'm sure many of you may have experienced this problem before, right? You're running your Mac OS or Windows OS, suddenly it becomes really slow and your hard disk light is flashing. That's essentially when you are doing some extensive I/O, input and output from disk. That's essentially when this happens. Okay? So this brings up this challenge of data transfer between main memory and disk. And what we care is the efficiency, right? We want to be able to retrieve data really efficiently. And in order to do that, we basically need to address these challenges. One is to try to avoid untimely data transfer, meaning try to avoid those data transfer that's really costly, and try to avoid unnecessary data transfer, meaning fetching data blocks you don't actually need. So how do we do that? The challenge is how do we do that? There are many ways of doing this, which we will highlight later on, such as disk scheduling, batching, buffer management, good file organizations. That's essentially what we'll be covering in later part of today's lecture, right? So this introduces these two layers in database systems called buffer management and disk space management. So disks and files, meaning this disk space management layer, they are responsible of organizing data into files, and they're responsible for reading blocks or writing blocks from and into these files. So from an abstraction point of view, all this disk space management provides to the higher layer is to be able to read a particular block and write a particular block. That makes sense? So I don't really care whether you are reading a student record or you are reading a department record or whatever, right? The abstraction view is that the higher layer comes down and tells me to fetch this particular data block. And I will go and fetch that block from disk and convert that to something that main memory can understand. Right? That's the abstraction view of what's going on. That's the read operation. It could be the write operation as well. The higher layer decides to update a student record, and that's been captured in a particular block. Then you tell the disk space manager to write this block back to some location. Right? So that's the abstraction view of what's going on here. So you may wonder why not we store everything in main memory. Obviously, the cost is too high to do that. Not only the cost is too high, meaning dollar per byte, there are also physical limitations on how big a memory you can have. I explained this, right? If you're using, for example, the latest i7 processor, the maximum memory size, memory address space you can index using i7 processor is only 64 gigabytes. In other words, even if you're willing to pay for 128 gigabytes, with the i7 processor, you are not able to do that. Right? So it's not only a matter of how much you are willing to pay. Right? Another issue is main memory is volatile, meaning if you lose power, data is gone. Right? So that obviously doesn't work for a database setting. So you need to store data somewhere on a permanent storage media, so that even if you shut down your system or your system has lost power, you are still able to bring those data back. So this is solution number one. I explain why this doesn't work. Okay. So this introduces the disk, and so I will use this picture to illustrate the property of the disk, then come back and emphasize some of the points in that slide. So this picture is a generalization of this picture, right? This picture here shows a single surface. However, in a real physical disk, you don't have just a single surface. What you have is this. You know, I should have bringing a physical disk with me, but it's like this big, and typically like this big, surface-wise, and this thick. Okay. So inside that disk, what it looks like is this. You have a spindle in the middle that rotates all the time, and then you have multiple what we call platters, multiple platters, and each platter typically is double surfaced. The upper layer and lower layer, they are double surfaced. The surface, each surface is essentially a magnetic field that's able to store your data using this magnetic charged field, right? North or the other direction, right? Representing 1 or 0. Okay? And each surface, as I explained before, is organized into multiple tracks. Each track is nothing else but all these surface areas that have the same radius to the central spindle. Now each track is further divided into what we call multiple sectors. So each of this is a single sector, by the way. Sector is the smallest unit on a hard drive disk. Typical size for a sector is 512 bytes. However, that's not the smallest unit that database system of your file system operates over. Your database system or your file system operates over the smallest unit called block. Each block is multiple consecutive sectors. For example, if I tell you my block size is 4 kilobytes, that means it's 8 consecutive sectors of 512 bytes each. That make sense? You may wonder if the smallest unit is block, why people still care about an even smaller unit called sector. That's because beneath your file system or your database system, there's a lower layer called block device driver. That's the driver the hard drive manufacturer has written to interface with hard disk. In the block device driver layer, the smallest unit they operate on is typically sector rather than block. Okay? But we are not going to dive into the block device driver layer. We will stay on top of that. And typically in that layer, in the layer on top, the smallest unit you operate over is in this unit of block, which is either 4 kilobytes or 8 kilobytes. Sometimes it could be as big as 16 kilobytes.
So does the ARM then write only blocks and sectors?
Yes, I will come to that point. Yes.
So is there an inherent advantage to either having bigger sectors or smaller sectors?
Yes, of course there is advantage and disadvantage either way. I will explain this later on. Okay. All right. Now, how hard drive works? Essentially, you have this what we call ARM assembly. This guy does not rotate. This guy only moves in and out. So it does only one movement, in and out. Stretch the arm or retract the arm. You have multiple arms. Essentially, you have basically two arms per platter. One for the upper surface, one for the lower surface. Okay? The head of the arm, this black region right here. The head of arm is a specially designed physical component that's able to detect the magnetic field of the underlying sector. Of course, within one sector you have multiple magnetic fields. It's not just a single magnetic field. It has a tons of magnetic fields. This black region is able to detect whether it's north or the other direction, and is able to convert that to electrons positively charged or not, which essentially is how bits are represented in main memory. And then this is transferred back through the ARM assembly to your memory bus, all the way to your memory. So far so good? Okay? So the way you're going to read data from disk is the following. You're going to move the ARM assembly in and out to align the head of the ARM to the track that you try to read data from. Then you simply wait for the track to rotate so that the first sector of the first block that you're trying to read is aligned right below the head of the ARM. Then you start transferring those data while this is keep rotating. That's essentially how it does the magic. Yes.
Is that data transferred through the ARM itself then?
Yes, there's the memory bus going through the ARM and assembly, then through the memory bus all the way to the memory. Yes. Okay. So this is another view of it. So one point I want to highlight is the sector size is determined by the disk manufacturer. So it's fixed at the time the disk was manufactured. Typically it's 512 bytes. The block size is a logical unit. It's not a quote-unquote physical unit. It's a logical unit that defined by your system, by your code. So for most database systems, they define block in either 4 kilobytes or 8 kilobytes. There is a trade-off, as what one of you asked this question, which I will explain it now. What's the trade-off? But it's a logical unit, meaning block size is not necessarily fixed. It can be changed if you update your code. But sector size, you can do nothing about it. That's manufacturer dependent. Okay, that's manufacturer dependent. Okay, so component read, essentially that's what I have just explained. These are some typical values. So you're accessing a disk page involving the following components. One is called seek time. The seek time refers to the time it takes to move the arms to position disk head on the right track, meaning in and out. This is the seek time. So in other words, this is your seek time. This is your seek time. Okay? This is your seek time. The second cost is what we call rotation delay. Seek time basically is the time it takes you to move the head arm to the right track. But then you have to wait for the track to rotate so that the block you're trying to read is aligned with the head of the arm. That takes time. Right? What's the best case scenario and what's the worst case scenario? Can someone tell me? Yes?
Best case scenario is on the interior disk, and the worst would be at the exterior.
Yes. In other words, the best case scenario is once you finish paying the seek time delay, meaning you move the head of the arm to the right track, you are so lucky the data you're trying to read has just been rotated right below the head of the arm. You can start reading right away. So your rotation delay is 0. You don't wait for any rotation. The worst case is what? Once you move the head of the arm to the right track, the block you're trying to read has just finished rotating over that particular position. You have to wait for a whole rotation before you can start reading data from that block. That's the worst case. Does that make sense? So what's the rotation delay? Well, rotation delay is an average notion. On average, what do you do? On average, the block can be anywhere on this circle, right? So on average, you wait for half rotation. Yes?
Are you guaranteed to have all the blocks, like reading specific sectors? Will the block that you need to read be in sequence? So if you start at this sector, it'll end at this sector?
A block is always a consecutive collection of sectors. That makes sense? So that answers your question, right? Yeah, so it's always a consecutive sequence of sectors from the same track. So rotation delay capture this average delay that you have to wait for rotating the block you're trying to read to align to the head of the arm, so it's half rotation. Then finally, there is a transfer time delay. Transfer time is moving data from the surface to memory, right? So this is essentially the time it takes for the head of the arm to read the magnetic field and convert that to positively charged electrons. That takes some time. So that's what we call the transfer time delay. So reading data from disk involve essentially these three components. Typical values for this are seek time is typically between 0.1 milliseconds to all the way to maybe, in the worst case, maybe 10 milliseconds. And this, if you compare this to the speed of reading data from main memory, this is way slower, almost 1,000 times slower, or at least 10, 100 times slower. Why is that? Because as we explained last time, reading data from memory is pretty much like transferring electrons over your memory. An electron move at the speed near to the speed of light. So it's really, really fast. Whereas this thing, the seek time, this is a mechanical structure. No matter how fast you can move, you cannot move as nearly as the speed of light. Yes, this can be really, really fast, but compared to the speed of light, is super slow. It's super slow. So does the rotation delay. It's also a mechanical movement. Henceforth, the speed of that is way slower than the speed of light. Okay, that actually already explained why reading data from disk is much slower than reading data from your main memory. Because one is mechanical speed, the other is almost the speed of the light. Obviously, there's a huge difference, right? If you think about that. So seek time typically is 0.1 to maybe 10 milliseconds. You can typically get this value from the surface of your hard drive. When you purchase a hard drive, there's the sticker. They actually tells you what's the seek time of my hard drive. Now you know what a seek time means. It means that the average time to move in and out your arm, okay, to different tracks. Rotation delay. So if you go to, for example, so you look at any hard drive, so they all give you this number here, right? Have you guys ever paid attention to this number before? I mean, you should. If you're buying this, you should. If not, you should start paying attention to that starting from today. Can someone tell me what this means?
How fast the disk spins?
How fast it spins, yes. But what RPM stands for, do you know?
Revolutions per minute.
Revolution per minute or rotation per minute. Why rotation per minute tells you how fast it spins and why that's important. Now, with today's lecture, I hope you now realize this is essentially this rotation delay. That number tells you the rotation delay of that hard drive. Why is that? What's the rotation delay? I just said, typically we just use the average case, right, which is half rotation, time to take to do half rotation, right? I just explained that, right? If I tell you the hard drive is, in that particular case, okay? So typically they will also tell you the seek time delay somewhere here on our speaker. Now, why this tells you the rotation delay? This basically tells you you do 7,200 rotations per minute. Right? In other words, you do this many rotations in 60 seconds. Now, how long does it take to do one rotation? Essentially, 60 divided by that. That's how long it takes to do one rotation in seconds, right? Does that make sense? You do the math of that. That's about 8 milliseconds. That's about 8 milliseconds. So the rotation delay is what? What's the rotation delay for this disk? 4 seconds, right? Half of that. You do half rotation. Right? On average, you wait for half rotation. Okay? So rotation delay is typically between 0 to 6 milliseconds. In this particular disk, that's 4 milliseconds. So next time when you buy this, pay attention to this value. Most disks today come with this value. Most disks come with this value. The higher this number is, the better it is. But more expensive it is, of course. Transfer rate is about 0.008 millisecond per 8K block. So transfer rate is really fast, which means when you are trying to calculate the delay of how costly it is to read data from disk, it's typically dominated by seek time and rotation delay. Right? That makes sense? Because the transfer time is orders of magnitude faster than the other two. So the bottleneck is typically not on the transfer time, it's really on those mechanical delays, seek time and rotation delay. Transfer time only matters if you're reading a large number of blocks, because this is a small value for one block, but when you're reading multiple, like tons of blocks, they accumulate up to some value that might be significant. Does that make sense? Okay. So this is a typical example. The latency, I just did this calculation, so that's how we did it. Okay. So that's the rotation. Next, I'm going to answer some of the questions you guys raised, which is arranging pages on disk. By the way, in this class, in this lecture, page and block are the same concept, right? When I say a page, it means the same thing as a block. It's essentially 4 kilobytes or 8 kilobytes of data, right? Organized into a unit. Either page or block, they refer to the same thing. So how do I arrange pages or blocks on disk? So the concept is the following. When I say next block, what do I mean? Because of this particular structure that this has, you want to minimize, if you think about it, when you are organizing data on disk, given the properties we have just discussed, you want to make sure the data you're reading from disk are consecutive to each other. Why is that? Why is that important? Because that makes sure when you are moving from one block to the next block, you are not paying another seek time and rotation delay. Does that make sense? If I'm reading 2 blocks next to each other on the same track, I pay 1 seek time delay, 1 rotation delay, then I just sit there, wait for them to be rotated and read them continuously. Versus reading 2 blocks, 1 block here, 1 block here, I need to pay 1 seek time, 1 rotation delay to get the first block. Then I need to move my disk again to pay another seek time and another rotation delay to get the second block. Does that make sense? The latter approach obviously is way more expensive. Henceforth, when you are writing data back to disk, you try to increase this thing called locality. For that reason, we refer to the concept of next block. So next block on disk refers to blocks on the same track, meaning first block, second block, all on the same track. When you run out of all blocks on one track, followed by block on the same cylinder, what do I mean by cylinder, by the way? Cylinder is a conceptual concept. All the tracks with the same radius to the center from different platters form a cylinder. So that's a cylinder right there. Okay? So you may wonder why the next block, when I run out of blocks from the same track, next block refer to the next block from the next track of the same cylinder. Why not do this? Why not expand to the next track on the same surface? Why do I go down instead of going out?
Or you set the arm
That's
Battery, so the motor.
yes. When you set the arm on one track, you set the arm, all these arms to the same cylinder, to the tracks on the same cylinder. So if you define the next block as coming out from the next track of the same cylinder, you don't pay another safe time delay. You don't have to move your arm. Okay? When you run out of tracks on the same cylinder, now you move out to the next cylinder. Now you have to move your arm. Now you have to move your arm. If you read enough data, sequentially reading data, now you need to move your arm. Does that make sense? Okay. So with this concept in mind, you obviously want to make sure blocks in a file should be arranged sequentially on disk, meaning next to each other. So Windows used to have this operation, I think they still do, called disk defragmentation. It's recommended you do that from time to time. The reason actually is, over time, blocks or pages of the same file may no longer stay next to each other because of deletion and insertion, so that they are fragmented, quote unquote. So the defragmentation process is to put them back to sequential blocks on disk, so that disk performance improves dramatically as a result of that. Okay? Does that make sense? For sequential scan, if you know you're doing a sequential scan, you're reading multiple blocks sequentially on disk, this concept of prefetching become really useful. Meaning, even though you're reading just this one block, if I predict you're going to read the next few blocks, you know what? I will go ahead and read them. Why that's useful? Because if you write your code in such a way, this signifies how you should write your code, by the way. Let me tell you two ways of writing your code, right? Suppose you want to give 6% interest on all records. There are two ways of doing this. One is fetch the first record, give 6% interest, read the next record, give 6% interest, and so on and so forth. Okay, option one. Option two, fetch all records at once, cache them in memory, give them 6% interest one by one. Do you follow me? Which will be more efficient and why? Which approach is more efficient and why? Yes, Blake?
The second approach?
Yes, why?
Because you avoid having to move the arm on the disk 2 times, you just do it once, and then...
Yes, essentially that's what happened, but precisely to elaborate your point, right? In the first approach, what happens? You read the first record, which is in a block, you fetch the block. Now you do something with your CPU. While you're doing that computation, disk is keep rotating. So by the time you come back for the next record, that block is gone. You have to wait for it to be rotated back. Does that make sense? Then this happened to the third record, fourth record, so on and so forth. Do you follow me? Whereas in the second approach, I move my arm, I read the first record, then I read all of them in sequential, I cache them in memory, now this rotate, whatever, I don't care, I do my computation. So this is kind of the concept of, so nowadays, today's disk is really smart. If you write your code like the first approach, the compiler and the disk block device driver will be smart enough to figure out, okay, you are going to fetch those records anyway. Even though your code is written in this manner, I'm going to pre-fetch them all for you so that they're ready for you to use when you come back to do the next computation. So you don't have to wait for another rotation delay. Of course, one slight adjustment I will make to the statement I just made is that when you are doing this interest example over records, multiple records typically reside on the same block. Each block holds not just one record, each block may hold multiple records. Does that make sense? So when you read the first record, you are not reading just the one record, you're reading the block holding that record. Which, let's say each block holds 10 records. While that maybe block is 4 kilobytes, each record is 400 bytes. So that's 10 records per block. So I'm reading the first block, I got 10 records. So for the next 10 computation, I'm fine because this block data is in memory. But when you come back for the 11th record, you need to fetch that second block, but by the time you come back, it's gone, it's rotated away. You have to wait for it. In the second approach, I read multiple blocks, so I have hundreds of records ready for you to use, even before you send the request of reading them. So obviously there's a gain over there. You avoid the rotation delay when you're moving from one block to the next block. Okay? Yes?
So if you're reading a huge piece of data, then would all the arms that are stacked in the same cylinder start prefetching even though you're not technically on that block? Right?
Good question. What you're essentially asking is how aggressive I should be in prefetching. Should I prefetching only data from the same track, or should I prefetching, since my arms are aligned with all the tracks in the same cylinder, should I prefetching all the blocks from the cylinder? There's no good answer for this, right? Because if you're too aggressive in prefetching, maybe you prefetch too much data than what's needed, and as a result, you blow up your memory size. Your memory size, keep in mind, memory size is limited. All the stuff you prefetch, you have to store them somewhere. This is somewhat similar to if you install a solar panel on your house. They generate a lot of electricity, right? No? But the electricity grid has a capacity. If everyone starts installing solar panel, the city will have a problem because electricity, I don't know whether you guys know this or not, electricity is really hard to store. There's no way of storing electricity as for now. The only way you can store electricity is to move them around in the grid. If everyone starts generating so much electricity using their solar panel, the city will have a problem. That make sense? The same thing here. If you prefetch too much, it overflows your memory, you have a problem. So that decision, we will talk about how to make that decision later on. Okay? So I show you some experiments we have run. Okay? So in this case, I'm using this particular block device driver that in this case, this is the time of your execution. The y-axis is the offset in bytes. So I start at a particular position, I count how far I'm reading away from that position in bytes. That's called offset value, right? In this case, I'm running a single workload called SDB rate. This is a sequential rate workload, as you can tell from the offset position, right? Obviously, it's a sequential rate because offset is continuously increasing, so that obviously signifies a sequential rate. Does that make sense? Okay, so this is a sequential rate. Now I'm adding a random rate workload. DD is a sequential workload. RR is a random rate workload. How can I tell that? Well, that's because if you look at the offset locations, clearly I still have that sequential rate operation. I can tell, right? I can tell that. That's a sequential rate operation. But in addition to that, I see many random dots all over the place. They do not follow any particular pattern. That must be a random rate workload. Because your offset location jump all over the place. You're moving your arms back and forth to different locations. Do you follow me? Yes? Okay? What's interesting to note though is, for the same amount of time, let's say 100 seconds into this workload, in this case, I'm able to read almost 60,000 megabytes in terms of how far I'm reaching out, right? That tells me how far I have, how many data I have read. That same workload, once you inject a random rate workload to run concurrently with that sequential rate, what happens? For 100 seconds, you read much less data than that sequential workload alone. Do you notice that? Right? The amount of data, if you look at the amount of data you're reading, is only what? 57,000 or something, right? Much less than what you are able to read in sequential rate workload by itself. The gradient is you are moving arms back and forth due to that random rate, serving that random rate. If I keep doing this experiment, now I inject 2 random rate workloads. What do you notice from this picture? I'm still running that sequential workload, by the way. You will notice that, what happens? You don't even have that sequential workload. That sequential workload is no longer even noticeable from this output. Why is that? Because you are serving these guys, these 3 requests in a kind of like a round-robin fashion, right? You serve this sequential workload a little bit, serve the first random rate workload, serve the second random rate, then come back to the sequential workload. Because of that, that sequential workload is no longer sequential. Because by the time you come back, the arm is at a different location due to the serve of that random workload. Does that make sense? You wonder what's the purpose of this experiment, right? Nowadays, a lot of people move everything to the cloud, right? You run some virtual machine from Amazon AWS. But virtual machine is not a physical machine. It's a virtualized resources. You have multiple VM running on the same server, physical server. So they share the same physical disk. It could be the case that I'm running a sequential workload on my VM. I should be able to finish my job in an hour because the sequential workload is really fast. So I pay Amazon for 1 hour usage of resources. Amazon may hire this guy, say, okay, I will co-locate your VM to the same VM that Feifei is running, a sequential workload. Why don't you just do some random rate? You guys are 2 separate VM but running on the same physical disk. Because of that, Feifei's workload that should have taken just 1 hour now will take 10 hours. And why Amazon is interested in doing this? Obviously, you profit is 10 times more for the same workload. Does that make sense? Yeah, the sequential workload that should finish in 1 hour now will end up taking 10 hours. So the user pays more. So this brings up this important issue in cloud, which is fairness. Right? How do you ensure fairness when you are executing your workload on the cloud, when you're paying them for their resources? Right? So if I run 4 random rate with 1 sequential rate, you can no longer even tell where that sequential rate is. And this is evident from this picture where I show the bandwidth, meaning how many bytes you are reading per second for that. When you have 1 sequential workload alone, it's very consistent, almost 70 megabytes per second. You are reading data from disk. But when you have 1 sequential with 4 random rate, it drops to less than 10 megabytes per second. That's the speed of your workload. Okay. So that summarizes the disk space management part. Next, we're going to talk about buffer management. Yes, go ahead.
The random reads are just like something else the OS is doing, right?
Just jumping off to different locations on this. Like 1 block here, the other block there, so on and so forth. Okay. Now, next we're going to talk about buffer management. All this data you read from this must be quote-unquote cached in main memory, right? Cached in main memory. But your main memory size is limited. It's not unlimited. Furthermore, this main memory space is shared by the operating system and other processes running on that operating system. It's not owned by the DBMS alone, right? If my machine has 12 gigabytes of RAM and I'm running a database server on this machine, it doesn't mean the database server will have all 12 gigabytes of RAM to it, because you have to reserve some memory space for your operating system and some memory for other processes running on that same operating system, on the same machine. Okay? So typically what happens is you will specify how much memory you will allocate to a particular database server instance. Right? So let me see whether I can show you that really quick. So in this case, I actually didn't specify the buffer size, but I just use the default setup of MySQL. But you, as a database administrator, you can actually specify the buffer size used for different processes within a database server. Right? That's essentially specify how big the buffer size is available for that particular process within your database server is available to use. You cannot use more than that, essentially. And these values, as a database administrator, how do you set up these values? Well, you set these values depending on how big your data is and how big of a RAM space you have on that particular server machine. Okay? It used to be these values are set by human beings. That's part of the reason why DBA actually make a lot of money, because there's no golden rule to follow, right? How to set these values. So what happened is, over the years of experience, DBAs trained like some heuristics not only to their mind, they know how to do this, they just set this value somehow magically. But imagine you have many such values to set, right? This is a really high dimensional space. This parameter space is huge. How do you know you are setting this value properly to gain the best possible performance? Do you follow me? And that's a very interesting problem. This is called auto-tuning of your database. Meaning setting these values properly in a really high dimensional space and adjust that dynamically over time. And just fairly recently, starting last year, people have been doing some really interesting work in this space using machine learning techniques, using deep learning and all that, to set these values automatically. It's called database that learns by itself over time. Okay, so those are really interesting discussions that I'm not able to get into. Okay. Now, coming back here, so imagine I have a buffer size that's specified by that configuration file, right? Tells you how big the buffer is. Instead of viewing the buffer in bytes, I'm gonna view this buffer in blocks. Okay? So 128 megabytes is translated to I don't know how many blocks. Once you tell me the block size, I just use 128 megabytes divided by that block size. That tell me how many blocks I will have. So each of this is a block or a page, right? Either 4 kilobytes or 8 kilobytes. You follow me? Okay? Initially, your buffer is empty. Over time, these frames will be occupied by data you fetch from the disk. So a black frame represents a frame that's currently occupied by a page or block you have fetched from disk. A white frame represents that's a free available frame. Then nobody is using it at the moment. Okay? So the challenge now is, what's the dilemma? The dilemma is you have a huge number of disk pages, huge number of blocks on disk, but you only have a limited size of memory buffer. When you have that kind of setup, a challenge is to decide what blocks you should keep in memory and what blocks you should write back to disk to free up the memory for other blocks to use. Does that make sense? So that's essentially the challenge. And let's see how we do this. In order to do this, let's first understand the data structure we use to represent each frame in the buffer, each single frame in the buffer. The data structure is as follows. You have a frame number that tells you which frame it is, so 1, 2, 3, 4, so on and so forth, right? That's just a unique identifier for all the frames in the buffer. Page ID denotes if the frame is occupied by a particular page or block. What is the ID of that block or page? Okay? So for example, this could be, the first one could be page 10, then empty, then page 20, so on and so forth, right? So it tells you which page is occupying that particular frame. Pin count is something I will explain later. I will come back to this. Dirty is a Boolean flag to denote whether this page, this particular page that's sitting on this frame, has been modified since it was read from disk into memory. Why this is important? If dirty bit is set, meaning that I read this page from disk to main memory, and then I did some update to this page. If the dirty bit is set, I need to make sure I write this page back to disk, so that the change is permanently reflected on disk. Does that make sense? Otherwise, if dirty bit is not set, meaning it's a read-only process, I fetch the page, I read the value of it, I do something with it, but I never come back and update records on this page, you don't have to worry about writing this page back to disk because the content of the page on disk is still the same as the content of the cache version in the buffer. Okay? This has a huge implication to durability and atomicity for transactions. This has a huge implication to durability and atomicity for transaction. Why is that? What transaction says is when a transaction commits, all changes made by that transaction must be durable, right? Must be durable, meaning permanently reflect by your database. The challenge though is that by the time transaction commits, the changes made by that transaction may still reside in main memory buffer, has not been pushed back to disk. Does that make sense? If you don't do nothing about it, and transaction has committed, and later system crash, you lose everything in buffer, then you will lose those changes made by those committed transactions forever. That's a violation of the durability requirement. You follow this discussion? So what's a simple solution to that? Well, the naive solution will be, when transaction is ready to commit, what do? You search for all the dirty pages made dirty by that transaction, and push those dirty pages back to disk, then, only then, allow the transaction to commit. That's a naive solution. This naive solution, however, is not a good solution because if this particular transaction has made a lot of changes throughout its process, meaning a lot of dirty pages in the buffer for this transaction, then the committing process becomes really expensive for that transaction because you need to wait for the buffer to write all these pages back to disk. They may not be sequential writes. They could be blocks in random locations. So they could be random writes. That could be really, really slow. So transaction won't be able to commit only after a long time. Does that make sense? Real database system doesn't do this. How they solve this problem, I'm not going to talk about this in this class. But just keep in mind, this is a challenge. Why this has to do with atomicity? Atomicity says, when transaction commits, all changes must be reflected, but when transaction aborts, it must be like nothing has happened before. Imagine a case where transaction has made a bunch of changes. There are dirty pages, they are cached in buffer. However, some of them, for whatever reason, has been written back to disk. Some others, dirty pages, are still residing in the buffer, they haven't been written back to disk. Now transactions, for whatever reason, decide to abort. For those dirty pages that are still residing in the buffer and never been written back to disk, you are fine. You just throw away those dirty pages. Does that make sense? It's very easy to undo the effect of that transaction by just throwing away the dirty pages in buffer. But what about those dirty pages by this transaction, but they have been written back to disk by the buffer manager? Now it's really hard, right? Because you lost what the original content of that block looks like, because it's been overwritten by this dirty page of an uncommitted transaction, and later decide to abort. Can you somehow magically restore the page being written over on disk? That's a big question mark, right? But you need to do that to ensure atomicity. How do we do that? I will throw that out as a question. The time we have on this class is just not enough for me to discuss that in details. Okay? With that being said, I'm ready to explain what the pin count means. you don't have just one transaction accessing the buffer at a single page. It's possible that multiple transactions ask for the same page. You read the value A, I also read the value A. You write the value A, I may also need to read, update the value A or write another value of A. That make sense? So pin count is used by the buffer manager to keep track how many transactions are still using this current page. I need to know that. Why that's important? Because if I decide to throw away this page from buffer, I can only do that when pin count is 0, meaning there are no active transactions are still using this page. Then I can keep this page out of the buffer. Otherwise, if pin count is not 0, meaning at least there's one more transaction that's still actively using the page, I need to cache this page in the buffer. I cannot throw away. So pin count is used for that purposes. So to summarize, whenever a transaction requests a page in the buffer, you increase the pin count by 1. When that transaction aborts or commits, you decrement the pin count by 1. And when pin count goes down to 0, this page is ready to be removed from the buffer anytime, because no transactions are actively using this page anymore. Okay? And this is what we call pin the page and unpin the page. So the first time a transaction requests a page, you pin the page. When the transaction is done using that page, meaning abort or commit, you unpin the page. You unpin the page. So far so good?
When you pin a page, I'm just getting a little lost about why, if you have pages pinned so it equals 1, how can you unpin another page that, like, if you add more pages to it?
No, I don't get your question.
Oh, maybe I'm going.
So maybe we should take this offline. Basically, whenever a transaction is going to use this page, you pin the page. By pinning the page, what the buffer will do is check whether this page is cached in the buffer or not. If it's already there, it simply increase the pin count by 1. If it's not there, the buffer manager will go and fetch the page from disk, cache that in the buffer, increase the pin count by 1, and return the frame number to that transaction. So that's pin the page. Unpin the page means transaction done, commit or abort, come back, tell the buffer manager I'm done. Then for all the pages that were pinned by this transaction, the buffer manager will unpin those pages. Unpin is very simple, just decrement the corresponding pin count by 1. That's it. Okay? Here's what happens. Yes?
So does the database kernel have any idea what the scheduler is doing for the transactions? Because it's the sequential schedules of the transactions and borrow.
Well, the buffer manager the behavior of the buffer manager is agnostic to the scheduler you're talking about. Because from the eyes of the buffer manager, all I'm saying is, oh, you can't request them for this page. The particular sequence of that's not my business. I assume somebody else, the concurrency control scheduler component has already done a good job in ensuring the sequence of requests is serialized. That had nothing to do with my buffer manager's job.
Well, I was just thinking if multiple things had, like they were still in the buffer, but they were committed, you would have to like read the data in the buffer.
Well, no. The point is, the sequence of read and write requests coming to the buffer is produced by the concurrency control scheduler, which means they are serializable to begin with. So buffer manager doesn't need to worry about that issue. Does that make sense? Okay? Now, if your buffer is big enough, this model works. Whenever you need a page, you pin the page. When you pin the page, buffer will check if this page is already in the buffer. If so, increase the pin count by 1. If not, the buffer will, on your behalf, go fetch the page from disk, cache in one of the frame, return the frame number to you. Now you can basically read the content of this page from that frame. So that's the pin page process, right? There is a challenge though. The challenge is when you pin a page, it's not in the buffer. So buffer manager go fetch that page for you from disk. come back, what happens? What happens? There's no space, there's no frame available to hold that page. You go all the way fetch the page, somebody is pinning that page, you go fetch the page, but there's no space in the buffer. There's no available frame in the buffer. Does that make sense? What do you do in this case? What do you do in this case? Well, this brings up the interesting problem of buffer replacement. So let me illustrate this using a very simple example. So suppose this is my buffer. And my buffer has, let's say 5. 1, 2. This is my frame number. I have 5 frames. So it's a really simple case. Now this is my disk. On disk, let's say I have 6 pages. And these are not necessarily sequential pages, right? They could be somewhere. So 3 of them are here. Then 2 of them are here. Then there's 1 more here. Okay? Those are page IDs. Page IDs. So far so good? So what I'm going to do is somebody comes in, a transaction comes in, and I'm going to pin the following pages. I'm going to pin P1. What do you do? When you pin P1, you ask buffer, do you have P1 somewhere? The buffer says, no, don't worry, I will go fetch P1. So you move the arm, rotate, blah, 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 slow, but wait until you come back. You come back with P1. So this is sync time, rotation time, plus transfer time. You got it. Does that make sense? Yes?
Let's say string.
Huh?
What does the str say?
STR.
Why the cylinder? Yeah. What is that?
Sync time, rotation time, transfer time.
Oh, okay.
Okay. Now, this P1 must be placed somewhere, right? Let's assume we go with the smallest frame that's available. The frame with the smallest ID that's available. So you will place P1 here on frame number 1. And 30-bit is what? 30-bit is set to 0. And pin count, let's assume this transaction is doing a read-only operation on this page, which means I will increase the pin count to 1, but immediately after I have read the content of the page, I know I no longer need this page, so I will unpin it right after it. You follow me? I just need to read the content of the page. I know I'm not going to write anything back. I don't need this page anymore. I only need to read it once. So I pin it and unpin it. So the pin count will increase to 1 and decrement to 0 immediately. Does that make sense?
Why pin it at all if you're just reading the contents and you're not?
Well, you have to pin it, right? Pin means that tell the buffer to find the page for you. So similarly, I'm going to do the same thing for P2, P3, P4, and P5. So what happens? You're going to just keep doing this. Right? So far, no surprise. It's the same person, right? Now what's interesting is next I'm going to do P6. So you go and you fetch P6. Now what happens? What happens now? What happens now? You do not have space. Right? You do not have available frames left. So what do? You have to choose a frame to store this new page P6. Now, first of all, you can only choose those frames with pin count equal to 0 to replace. But in this particular example, the pin count is 0 for all of them. Because you pin them, you unpin them immediately. That's essentially what we have done. So you can choose to replace any of this, right? This LRU policy, least recently used policy, the name is self-explaining, right? Least recently used policy. What does it mean? Can you tell me? Yes.
It removes the block that was last used.
The last use, which block in this case? Can you tell me?
P1.
P1, yes. Because this was the furthest back in history that was used. So we'll replace this with P6. You follow me? The intuition is that you are using a simple intuition, which is if you haven't been referenced for a while, the probability somebody will come back and ask for this page is very low. Right? If you haven't visited a park in a long time, most likely you're not going to visit that park in near future. However, I can construct a workload that defeats the very design of RU. Essentially, I'm going to ask for P1 next. When you ask for P1, what happens? Well, too bad, it was just replaced out of memory by P6. So you need to go and fetch P1 again from disk. That's an additional I/O. Now, which page you should replace? P2. You see how this game goes, right? I will ask for P2. So essentially, if you are using RRU in this case, you are making the worst decision possible. You are always replacing the frame, the page, that you're going to use next, which incur additional I/O every time you request for that. In contrast, let me use, instead of using RRU, I'm going to use MRU. Now what happens? Let's rewind and backtrack to this. Let's backtrack to this case. Now you're asking for P6. If you're using MRU, which page you will be replacing? P5. Now if you ask for P1, now what happens? Bingo, you find it here. The buffer will pin the page right there. You avoid, you don't have to do this. Visit to the disk. And so does P2, P3, P4. So you may argue, okay, let's use that MRU. Isn't that the perfect solution? However, if you tell me you're going to use MRU, what happens? Okay, instead of after P6, you said you're going to replace P6 with P1. So you're going to replace P5 with P6. If you tell me you're using MRU, instead of asking for P1, I'm going to ask for. So instead of going round robin, I'm going to go like this, zigzag. So I'm going to ask for P5. So you end up replacing P4. Then I'm going to ask for P4. You end up replacing P3. So you are replacing the page you request, the very next page you request. So if that's the case, if you know this is the sequence, which one you should use, by the way, which policy you should be using? You should switch back to RRU. Because when you are requesting for P5, you end up replacing this, P4 is still there, so on and so forth. Do you follow me? But how can you make this decision? In some sense, you are trying to predict the future, right? In the past, there's not really a good solution to this. People basically generally use one of these buffer replacement policies, RRU or MRU. And there's a reason why people use this, actually. There's a deep theoretical foundation for this. It is called online algorithm, which is to compare the performance of an online algorithm. All these are called online algorithm. You are making a decision in real time online. You don't know. You input ahead of time. Your input is given one at a time to you. You don't know the whole input sequence, which is what pages to be requested. You need to design an online algorithm for this. People have been measuring the performance of online algorithm using something called competitive ratio. You can Google this if you are interested. Competitive ratio. So the idea is as follows, right? If you go to, so excuse me, I have to use this example because the typically the only good example you have for online algorithm is gambling or betting, right? So if you go to Las Vegas, you know you play some bets on some game, it's online, right? They won't let you know what will be the output of a particular, for example, you throw the dice, you just bet it's bigger than 3 or smaller than 3. You have to make a decision ahead of knowing the result of it, right? But imagine you have a really nice casino that tells you this. Okay, I'm gonna tell you all the output sequence ahead of time. Okay? Isn't that really nice? And come up with a betting strategy if I tell you that, to maximize your profit. Even that is not a trivial problem. It's actually not a trivial problem. It's kind of like, in another way, if I tell you the stock sequence, let's see. If I give you this curve, imagine we were at 5 years ago, but I tell you this curve 5 years ago, what this will look like for the 5 years down the road. I gave you $1,000 to begin with. One simple strategy is, okay, buy Google stock, go play, have fun for 5 years, come back and sell it. You make good profit. Right? But you can do better. No? That's a simple strategy, right? What would be a better strategy? Buy it, sell it, wait, buy again, sell it. That makes sense? It's much better than just buy and wait and sell at the end of the day. Do you realize that? So even if I tell you the data ahead of time, it's not a simple game. Right, so next time when you go to casinos, if they tell you, I'm going to tell you all the output sequence, and let's bet. If you can maximize your profit, you win the casino. Otherwise, I win all the assets you have. Don't easily say yes. It's not a trivial problem, even if they tell you all the sequences. Now, this buffer replacement algorithm we have talked about is even harder. It's like I tell you what it looks like in one day, then you need to design an algorithm at this point. Should you buy or should you sell? You don't know what the next 5 years is going to look like. Right? So this competitive ratio basically says, I want to analyze the performance of the online algorithm versus the optimal offline algorithm. Suppose I tell you everything, what's the best you can do, and use that to quantify how well your online algorithm will behave. That's called competitive ratio. Okay, with that being said, I'm going to stop right here. Next lecture, I'm going to talk about, now we know DSpace Manager and Buffer Manager. Next lecture, we'll talk a little bit about how database system actually use these different components to effectively organize data and retrieve data back from disk and write data back to disk.